I hope you're ready for another great week of business statistics with your instructor, Dr. Todd Daniel.
Well, now we're going to repeat this frequency distribution and the descriptive statistics using quantitative data. We can still use simple frequency as we did before. So a simple frequency is the number of times that a score occurs. However, with quantitative data, what we tend to do, let's say we have scores that range from 1 to 100. We don't want a frequency table that's 100 column or 100 rows long. Instead, what we do is bin the data. We create little bins into which we place the data. So instead of counting how many ones occur and how many twos occur, we'll count how many scores from 1 to 5 occur. So 1 to 5 will be our first bin, and 6 to 10 will be our second bin. We create the bins, and we count how many scores occur within those bins. Well, how many bins should you use? The number of bins, the rule is between 5 and 20. I'll do an example later where I just use 4 bins. But 5 to 20, the 20, especially when you're using bar charts, that's where the 20 is going to be much more reasonable. In the examples that we'll be doing with a frequency table, keeping a fewer number of bins is probably going to be better. To determine the width of the bin, you would divide the difference between the largest and the smallest values. So take the high score minus the low score and divide that by the number of bins. So in a moment, I'm going to show you some data that ranges from 1 to 20. And then we're going to divide it into 5 bins. So what I'll do then is I'll create 4, or the range will be 1 to 4 for each bin, and that will create a total of 5 bins. To create this in Excel, we would use a pivot table. You would open up your data set in Excel. We're going to be using the number of toys owned for this example. That's a numeric variable, it's a continuous variable. And we would select Insert and then choose Pivot Table. It opens up this Create Pivot Table dialog box where we identify the range of the data that we'll be referring to, and that will be populated by default. In the case where I only have the one variable in this example, that's the only data that we'll be using. It's always good to put your cursor somewhere in that data, so anywhere in the column, then you click Insert Pivot Table, you get this, and just click OK. And now we have the pivot table fields. We only have the one variable, which is toys owned for this simplified example. So it will go both into the rows box and the values box. But the values box is where we get to decide, are we going to do percentages or something else? In this case, we're going to use counts. We want to know how many, simple frequency, how many times does the score between 1 and 4 occur in this data set. So we would set our values to counts. Then you get a table, pops up with all the rows and the counts. And what we want to do is simplify this table or clarify this table. You would right-click anywhere in the table and choose Group. That will pop up its own little dialog box. By default, Excel knows that we have scores ranging from 1 to 20. We want to create 5 bins, and so we're going to use groupings of 1 to 4, because if you divide 4 into 20, we get 5. There'll be 5 bins. Just remember, this is not the number of bins. This is how many scores in each bin. It's 1 to 4, right enough to scale. Click OK. The table simplifies, and now we have 1 to 4, 5 to 8, 9 to 12, and the number of scores, the simple frequency, for each of those categories. We also get the grand total of 50, which, as you recall, was the total number of participants in this data set. So that's how we do a frequency table with our continuous data. Now we need to find out how to make pictures of our continuous data. Instead of using a bar chart, we're going to use a histogram. The difference between the bar chart and the histogram is the bar chart, the bars do not touch, and in the histogram, the bars do touch. We will center the bar over the score on the x-axis. So for instance, if we have a score of 2, we would center the bar over the 2. And what that indicates are the real limits of the interval. If we were using scores that range from 1 to 10, a score of 2.2 would go into the 2 category, but a score of 2.8 would probably go into the 3 category, would round up. And so what we have by centering the bar is essentially we're saying scores from 1.5 to 2.4, those are the scores that belong in this particular bar. In order to do this in Excel, we would open up our data set. We would click on the pivot table. This is the same table that we created just a moment ago. Click on any cell in that pivot table and choose Insert Clustered Column. That pulls up these options. So we're going to insert that clustered column, and we get a bar chart. Now recall, we want a histogram. We don't want a bar chart, so we're going to need to edit this chart. We would do that by right-clicking on any of the bars in this chart. So you right-click, and you choose Format Data Series. That will give us a dialog box that has an option to change the gap width. We'll drop that all the way down to 0%. The gap between the bars is 0, and now we have the histogram. Now the bars do not, or the bars touch, the bars are connected. There's 0 gap between them. What are the advantages of a histogram? Histograms do something very important. They show us the shape of the distribution. And the shapes could be a normally distributed curve, but very often they are not normal. There's something that has deviated from normal. So we need to know how to talk about those non-normal curves or the deviations from normality. One thing we'll talk about in just a moment is skewness. This is what we saw with the previous histogram. We see all of the scores on one end of the distribution and very few on the other end of the distribution. So we see a highly skewed distribution. In this case, it's a right skew or a positive skew. We might also find bimodality. The mode is the most frequently occurring score. And in this example of a histogram, we see a lot of scores on the high end, a lot of scores on the low end, and not so many in the middle. We have very extreme answers here. We might also identify outliers. You notice the histogram bars are all clustered together, and then there's one that's just out here by itself. That is an outlier. It is an unusual score. It could be a data entry error, but it's a score that doesn't fit with the rest of that histogram. Sometimes it's a legitimate score, sometimes it's not. And depending upon the nature of the outlier, we may choose to leave it in or take it out. We may just simply delete it. We may trim the ends of the distribution by 5% on either end and just look at the middle 90%. So we have options for dealing with outliers, and I'll have an entire lecture on what we can do with outliers. That'll be coming up here in a few weeks. So again, back in the before days, I used to hand out pipe cleaners to everyone in class to play along with this next example. I'd give everybody pipe cleaners, and we could, I could hand them to you directly. I could stand right next to you and breathe in the same space where you are. Well, we can't do that now, so I'll just show you this example, and maybe you could just pretend that you have a pipe cleaner. In another example in the frequencies, I used to hand out M&Ms. I'd buy a bag of M&Ms, and we'd count the number of red ones and green ones and brown ones. And then you got to eat the M&Ms as I did the rest of the lecture. Again, we can't do that anymore either, but maybe someday. Let me return to the pipe cleaner. So obviously the pipe cleaner is just a straight line. And what I would have you do is bend it a little bit. We want to make a normal curve with this pipe cleaner. which is most of the scores are in the middle. So imagine an x-axis. We have most of our scores are in the middle, and then we have the tails. That's where the outliers or the fewer scores would be. So that's just a simple normal curve. Now the reason that I do this is I want to illustrate with something like skewness what has to be happening for us to have a skewed distribution. So in this case, we have scores that are pulled out to one end. What's happening is if we have an outlier on one end, it's going to pull our distribution that way. That's going to result in this skewed curve. A negatively skewed distribution is where we have most of our scores on the high end, and our outlier or our fewer extreme scores will be on the low end, the tail of the curve. If we're looking at the running speeds of football players, so we have a lot of very fast people, and then like I'd be in the outlier on the tail on this. I was not a very fast runner back when I played football. This is why I went into playing the tuba in the band, and then eventually went into statistics. Right? Not a good football player. I would be one of the slow outliers. Everyone else would finish, and then I'd come loping along. A positively skewed distribution is one where you have a lot of low frequencies and fewer high frequencies. So again, returning to our normal curve, we have a lot of scores on the low end. Let's say we're looking at reaction times, how long it takes for you to see a stimulus and respond to it. So we got a lot of very, very quick times, and then there's some people who are just a little slower, and they're pulling out that tail of the distribution. There we go. So creating what we call a positively skewed distribution. All the outliers are in the positive direction. Here is how to remember the direction of the skew, positive or negative. So you think about your x-axis. You have the positive end, you have the negative end. The end to which the tail is pulled out, that's the direction that we call the skew. So for instance, if it's pulled to the negative direction, we call it a negative skew. If it's pulled out to the positive direction, we call it a positive skew. Remember this from StatsCal, who will appear in several videos. StatsCal reminds us that the skew is in the tail. The tail of the distribution. Which end is pulled out? If it's pulled out to the negative end, it's a negative skew. Sometimes when people are new to this concept, they tend to look at the bulk of the curve. The skewness is the part that's not part of the bulk of the curve. It's the outlier, the extreme part. So the skew is in the tail, positive or negative. So let's reinforce this idea. As you look at this scale, is this a positively or negatively skewed curve? Positive skew, the tail is pulled out to the positive end. This also has an effect on the mean, median, and mode. The mode is the most frequently occurring score. It's the top of the curve. The mode will not change with the addition of outliers. That score will stay exactly the same. The median will be pulled out slightly in the direction of the outlier, usually by 1 or maybe 2 points, depending on how many outliers you have. But the mean could be greatly affected by the outlier. For example, if we were to try to calculate the average income of everybody in this room, and we ask you, how much was on your W-2 last year? But we happen to have one student who has been mining Bitcoin for years and years, or is an internet genius and has a website, and that person makes $1 million a year, and then the rest of us are making, well, that's about what you make, right? Okay, so the rest of us are making more, college salaries. Do you see how having one person with $1 million, we just average that out? And I say, hey, congratulations, the average income in this class is $90,000. And you say, that doesn't seem realistic, having seen my paycheck. One person, one outlier, could greatly skew the mean. It's not going to affect the mode, slightly affect the median. If we have skewed distributions, like housing prices, where you have most houses are in a certain range, but there's several small number of multi-million-dollar houses that skews the distribution, we're going to use the median for reporting those scores rather than the mean. Second example, is this a positively or negatively skewed distribution? It's a negatively skewed distribution. The tail is pulled out to the negative direction. The way that we can calculate the amount of skewness is by comparing the mean and the median. There's a formula for that. Now, we're going to see a calculation of skewness when we look at the descriptive statistics in JASP that'll be created for us. We can also do it in Excel, but it takes a lot more work. If you do it in JASP, you'll just see it appear. And we'll be able to make this comparison. And essentially what we want to know is our distribution too badly skewed for us to use? If it's really badly skewed, we might need to make some adjustments to the data, whether that's trimming the data or removing an outlier. We may need to adjust for that, and we have a way of determining whether or not that skew is too much. When we looked at the frequency table in JASP, we saw a cumulative frequency column. And I said that for nominal data, it doesn't really make sense to accumulate dog toys plus tennis balls. However, if we have something that can accumulate, whether that's an ordinal data or sometimes continuous data, the cumulative frequency can be very telling. So for example, if we have a play coming up in 2 months and we're all trying to sell tickets to get people to come to the play, we might want to keep track of how many tickets have been sold by week, but we also want to know the total amount of tickets that have been sold so far. We want a cumulative frequency. If we are tracking the number of fatalities each month since the beginning of the war, we see numbers higher or lower each month, but we also want to keep track of the total number of fatalities. Or, as has become very common, there's a pandemic, and we're tracing either the number of cases or the number of deaths. The cases are usually tracked with this simple frequency, so we can tell when there is a spike and when there is a decrease. We want to know the simple frequency, number of cases per day, and that tells us something about the trajectory of the outbreak. We're able to say, oh, it's getting worse or it's getting better by looking at that simple frequency. However, if we're tracking number of either cumulative cases or typically number of deaths, then we will use a cumulative frequency. So that is one where the steeper the curve, the more cases are being added, and as fewer cases are being added, we see it begin to flatline. The interpretation of the interpretation of a cumulative frequency graph is when it's concave curving up, that means the cases are increasing. If there is a constant rate of addition, we'll see a 45-degree line. And if the curve is concave going downwards, we see the number of cases are decreasing. However, cumulative frequency can never actually go down. If no new cases are added, it simply flatlines. It stays constant. So there's one more type of analysis that we want to explore. It's called a stem and leaf diagram. Now this may be one that you're unfamiliar with. It's not commonly used, but it is very useful within your analysis. Why is it not commonly used? This is more one of those behind the scenes kind of analyses. This is one that I would run very, very frequently. I don't think I've ever published one, so I wouldn't put it in a textbook unless I was talking about it specifically. I certainly wouldn't include it in a paper, but I would use it to help understand my data. So it's a very, very useful graph, probably the most useful that you've not heard of. That and also box plots, which we'll talk about next time. Before I tell you what a stem and leaf diagram is, let me show you the advantages and disadvantages of what we've already learned. So for instance, histograms, they show you the shape of the data. I was showing you skewness and kurtosis and bimodality. We get to see the shape of the data using our histogram. But what we've lost are the actual scores. So if I ask you how many people scored a 3, especially if those scores have been binned or banded, we've lost that entirely. Now remember, with our frequency tables, we kept the original scores. So if I want to know how many people scored a 3, it was 18. That's easy enough to find in that frequency table, but I can't tell much about the shape of the distribution from this frequency table. What the stem and leaf diagram does is give us the best of both, preserving the actual scores and showing us the shape of the distribution. To understand how this is being done, let me just take you back to something that you maybe learned in 3rd or 4th grade. Learning about numbers. And I remember learning about the tens place and the ones place and the hundreds place. So if I give you a single digit, that occupies the ones place in a number. And to make that make more sense, let me just add another number. I now have 79. 79 has a 7 in the tens place and a 9 in the ones place. At a third value, like an 8, this is 879. The 8 is in the hundreds, 7 is still in the 10, 9 is still in the ones place, and if I add another number, that's the thousandth place. What we're doing with a stem and leaf diagram is we're using the tens place and the ones place. So look at this stem and leaf diagram. The stem are values that in this case run from 1 to 9. I've actually doubled them up, 1 and 1 with an asterisk, 2 and 2 with an asterisk. I'll explain that in a moment. But these 1, 2, all the way through 9, those aren't 1 through 9, that's 10 through 90. And the leaves are in the ones place. So for instance, the lowest score here is a 1 in the tens place and a 4 in the ones place. That's a 14. I didn't have any scores until I got to 26, and the next score is a 29. Next is a 33. The highest score in this distribution is a 98. 1/4 would be 14. This 4, 3, 3, 4, that's 43, 44, 44. And if I ask you how many 44s are in this distribution, you now know there are 2. How many 65s are there? We go 60, 1, 2, 3, 4. There are 4 65s. 0 is still a number, so it just goes in the ones place. So we have 70, 70, 70, 70, 71, 71, 71. We're just using 0 to hold that ones place. And because these scores were limited in their range, what I did was I actually split the 1s and 2s, or let's say the 10s and the 20s. So what we have is, if you look at the 6, it doesn't have an asterisk. Those are values that run from 60 to 64. The 6 with the asterisk would include scores that range from 65 to 69. So I've simply split the scores 0 to 4 and 5 to 9. If I take my stem and leaf diagram and I rotate it, I essentially have a histogram where I can see the shape of that distribution. So I've preserved the original scores and I can see the shape. So you can see why this is a nice way of exploring your data on your own. As you as a statistician, you can explore, but you're probably not going to publish one of these. So that's why I say it's probably one of the more useful graphs you've never heard of. Excellent tool, but one that you'll not be seeing much in publication. The other, I'll say, disadvantage for something like this, it's easy to do in programs like SPSS. In Excel, you pretty much have to make it yourself. You have to add all of the stems and then add all of the leaves, and there's not a simple way of just examining a data set and say, boom, make me a stem and leaf diagram. Well, that is everything I have to tell you about categorical data and how we would describe them. Before we wrap up, you guys have any questions about what we've covered so far? Well, thank you so much for being here, and I will see you guys next week.